Hi, and welcome back to Codex. Today's speaker is Karlheinz Gröchenig from the University of Vienna. Professor Gröchenig is an expert in time frequency analysis, frame theory, and pseudodifferential operators. Today, he will tell us about the ability of the discrete Fourier transform to approximate the Fourier transform on the real line. Take it away, Charlie.
Well, thank you for the introduction. You sound like a professional speaker. I have to try to be on that level. So thank you for the invitation. It's been a long time that I have given an online talk. Reminds me of COVID with all its difficulties. So it's a bit ambivalent. So I will talk about something that you are all doing in numerical work. You have a function and want to compute its Fourier transform. Usually you do it via the discrete Fourier transform. So maybe 2 years ago, Martin Ehler, one of my co-authors on this work, taught numerical analysis. And he thought, well, what's actually happening? And we started to discuss. Later, Andreas Klotz joined the discussions. So this is joint work with Martin and Andreas on the approximation of Fourier transform via discrete Fourier transform. So here is the definition of Fourier transform. It's an integral on the real line. I use the normalization with a 2 pi in the exponent. And if you are given a function and you want to compute its Fourier transform numerically from the data, so the standard procedure is you sample the Fourier transform at positions j times h. H is the grid size, the increment, and say you center it around the origin. J runs from negative n half to n half with this precise inequality. So altogether you have n samples. The grid size of the increment is h. So n times h is the length of the sampled interval. So information about the function is on an interval of length L. According to the uncertainty principle, you can understand the Fourier transform only on, say, sets of length 1 over L. You will see the 1 over L appear later. So now that's basically the discrete information that you start with. Then you compute the discrete Fourier transform of that sample vector. So here is the definition of discrete Fourier transform. That's again a vector of length n. And the claim or the belief is that the output of the discrete Fourier transform at index k is related to the value of the correct Fourier transform at k over L. So the 1 over L comes, say, from the uncertainty principle. Now, if you do that, say, with MATLAB or whatever program you do to do the discrete Fourier transform, you actually get a function, and it's obtained by interpolating this vector linearly or whatever. So that's the numerical procedure. I wouldn't even call it an algorithm. That's the standard practice when you compute a Fourier transform based on a given function. You sample, do a discrete Fourier transform, and then you interpolate. And supposedly what you get is something that's related to the actual Fourier transform. So there is some plausibility up to that. And so the Fourier transform at k over L, so that's an integral. If you discretize the integral, say with trapezoidal rule, or say with Riemann sum, step size h, So here is the increment h outside. Then you get precisely this infinite sum. And then you truncate this sum, say, centered around the origin. And then what you get is, except for normalizations, the discrete Fourier transform. So there's some plausibility in this procedure. The first approximation is basically numerical integration. So if you want to estimate the error, you use the trapezoidal rule and error estimation. The second approximation is the truncation of an infinite series by means of a partial sum. So the question is, how fast does the partial sum convert to the infinite series? And okay, so that basically depends on the decay of the coefficients. So we'll see that decay properties will come in. Okay. So there are three important parameters that we should keep track of. One is the increment h, step size, mesh size increment. N is the number of samples that we use. And n times h, so the length of the sampled interval. That's sort of the size or the interval on which you have some information about the function. When we deal with error estimates, then numerical analysts usually give the errors in terms of the step size h. In complexity theory, they would often measure the errors in terms of the number of samples. And the question asked is slightly different. Basically, they search for the optimal approximation with a budget of n samples. So these are two slightly different questions. Okay, so once more, discrete Fourier transform, you have a vector of length n. Here is the definition of the discrete Fourier transform, Fourier matrix. The normalization is 1 over square root n, so that the discrete Fourier transform is actually a unitary transform. So the Fourier matrix normalized this way is unitary. So why is this great? Well, for certain dimensions, precisely when the dimension is a power of 2, there's a fast algorithm, the fast Fourier transform, or the Cooley-Tukey algorithm, well, already 60 years old. And that is a fast Fourier transform. So n samples, you have an algorithm of order n times log n operations. It's hard to beat that complexity. And just to spice up this talk, two citations. Fast Fourier transform is among the 10 most important numerical algorithms of the 20th century. That was stated in the year 2000, and Gil Strong called the fast Fourier transform the most important numerical algorithm of our lifetime. It's very interesting statements, maybe true for myself, but we are already a quarter of a century into the 21st century, so probably will be an interesting discussion. So what's happened since then? Fourier transform, discrete Fourier transform, and the fast Fourier transform algorithm are certainly a step in many, many algorithms. And whenever you deal with a fast algorithm, you're happy that you can reduce it or include a Fourier transform, because then you have at least one step that's very fast. So what do I want to talk about? So I have described the numerical procedure to compute an approximation of the actual Fourier transform from a sample of the original function. And the question is, okay, what does this procedure say about the Fourier transform? So I would like to make a distinction. One could ask and want to compute the value of the Fourier transform at a particular frequency psi. I mean, that's basically the numerics of oscillatory integrals. And you do the error analysis for a single integral. That's one question. So what we would like to understand better is, we want actually to understand the full Fourier transform f hat and get some feeling for the error and how the error depends on the increment h or the number of samples or the length of the sampled interval. So here we ask about the full Fourier transform and how it is approximated. That's different from just doing a single integral. There's a lot, or there's some work being done, but surprisingly little. So there are two classes of functions where there are earlier results. Compactly supported function with some smoothness that goes to Briggs and Henson, 95, to Charles Epstein, and I've emphasized the first name, just so there are no confusion. In a high-profile paper in Communications in Pure and Applied Math, there are some error estimates for exponentially decaying functions, but with very, say, stringent boundary conditions. In a very interesting owner's manual for the discrete Fourier transform, you could say whenever you approximate an integral, the error analysis is via the trapezoidal rule. Tons of literature on that. What's interesting, however, is the generic function class for which the trapezoidal rule is analyzed is analytic on a strip around the real axis. So for numerical analysts, or for a large group of numerical analysts, that's the generic assumption. And Martin found a citation from 2010 that beyond analyticity doesn't exist. A general theory. Well, I would say in our work we disagree with that, because we could rewrite our paper and do such an error analysis for trapezoidal rule. There's something very interesting by Auslander and Grünbaum, even earlier. They do an error analysis for arbitrary L2 functions, where you can either take pointwise evaluations, so they take local averages, and then it's basically an experimental paper. And there is an approximation in this context of numerical analysis with a cardinal sign by Frank Stenger. I will say a little bit about that later. And just a few weeks ago, when our paper appeared, Mario Ulrich sent me a paper where they looked at evaluating a single value of the Fourier transform for a function with compact support. So then it's precisely the procedure I described: sampling, discrete Fourier transform. And for functions with infinite support, they actually propose a different algorithm that might actually do better than what I present, but it's not what a standard numerical analyst would do to compute the Fourier transform. Okay, so let's get serious. And so some notation. And so to avoid the index set, so integers between negative n-half and n-half, I use bracket n. So that reminds us we have n samples. So for the sampled version of a function, I use f sub hn. So that gives us information of f sampled at step size h. We have n samples, and we have symmetry around the origin. The other parameter is the length of the sample intervals. So we have n samples, equidistantly sampled with distance h. So n times h is this length of the sample interval. Now, important, the error measure. Well, we're dealing with a unitary transform, so we measure the error in the L2 norm. Here once more, here is the sampled version of the Fourier transform at k over L. So what you see here in this notation, so 1 over square root L inside, this is the sample version, step size 1 over L, and n samples. And here we have the discrete Fourier transform. So a square root h would go to the f, then that's the sample version of f. And so what's left is a square root h over square root L, and that's precisely 1 over square root n. So I understand that these normalizations are hard to follow at first sight. The normalization is plausible when you think of discretizing the L2 norm. Okay, squaring this, we would get an h. And so that's plausible. And secondly, this error measure here has a nice symmetry. Okay, so this is the main object. That's the error approximating the sampled version of the Fourier transform via the discrete Fourier transform of samples of f. And the normalization makes sense because then we have a perfect symmetry. The approximation error, when we compute or approximate the Fourier transform of f, step size h, n samples, is the same as when we do the inverse Fourier transform to approximate f from f hat, step size 1 over L, and also n samples. So there's a symmetry in time and frequency, something we love in Vienna, of course. So, this is the error spelled out, and the short notation, it's this here, and the short notation is convenient. But I encourage you to keep track of the meaning, step size, and number of samples of this function. And here we have the discrete Fourier transform, samples of f, step size h, n samples, and this is the L2 norm of the vector. So this is really the complete discrete Fourier transform and the error of that. So comes the, let's say, the main result, 2025, appeared a month ago. So the main result says, if f has polynomial decay, and the Fourier transform is assumed to have polynomial decay, here parameter A, Fourier transform parameter B. So these are the assumptions. So for a harmonic analyst, polynomial decay is perhaps a more natural and perhaps more generic assumption than analyticity on a strip, which amounts to exponential decay of Fourier transform. So for us, that's a more natural assumption. It's certainly a much, much more general assumption than analyticity. So these are the assumptions, and the conclusion is, well, adjust the parameter slightly. So decay parameter A minus 1/2 minus some epsilon. Decay parameter B minus 1/2 minus epsilon. Then the error made by the numerical procedure is of the order L to the negative alpha plus H to the beta. So beta is anything less than B minus 1/2. Alpha is less than anything like B, A minus 1/2. Alternatively, if you want to keep A and B, then for every epsilon, there is a constant so that the error is to the order L to the minus A plus 1/2 plus epsilon, H to the B minus 1/2 minus epsilon. But I want to keep the alpha and beta for later. The constant here will depend on the epsilon or on which alpha we choose, but it's independent of the discretization procedure. And if I don't want to write the constant all the time, I use the less than tilde notation. So this symbol means here f of x is less than or equal to some constant times 1 plus x to the negative a for all x. So decay on the function and on the Fourier transform implies an error estimate. And before we move on, I want to give you some hints where this error estimate comes from and show you some mathematics. It's not very deep. What we added was probably our knowledge of time frequency symmetry and of function spaces. So the function spaces we use in Vienna all the time. Poisson summation formula was always used when in the error analysis or in other references. So I write it here. So Poisson summation formula says periodization of a function can be expressed by a Fourier series when you use the Fourier transform, evaluation of the Fourier transform as coefficients. I write this for the periodization of the Fourier transform. Okay, its Fourier transform is f with a reflection. So this is the Poisson summation formula. Here we have period 1 over h, and here we have a Fourier series. Period is also 1 over h, and that's the correct normalization. Now let's evaluate the Poisson summation formula at k over L. That's k over h times n. Now let's plug in. The decay conditions on f and f hat will guarantee that the Poisson summation formula is applicable pointwise for all x with absolute convergence of the sum. And actually, we can assume that both f and f hat are continuous. Okay, so I didn't say that before, but when we apply Poisson summation formula, okay, we make all these assumptions. So let's plug in k over L here and here. If I plug in k over L, so L is h times n, I see that the h cancels and I have a capital N in the denominator. So that's exactly what we saw when we discretized the integral for the Fourier transform, this here. And now I use periodization. So the sum is over J. I split the summation into residues, modulo n, and take a sum over n. So this J here becomes J plus M times n. J runs now through a residue class, negative n half to n half. And here we have multiples of this n. This does not affect the exponential, okay? If the n times m disappears. And so when I rewrite this expression, I have the periodization of f with period n times h. So that's period L. The periodization with period L evaluated at the point j times h. So this inner expression is the periodization at j times h. I keep the h here, and I keep that here. So, in other words, if I just keep rewriting the right-hand side, I get, so I see that this here is actually the sampling of the periodization at hj. So step width h. 1 squared h goes into this notation, and 1 squared h remains. And then we take the discrete Fourier transform of this periodization. That's the discrete Fourier transform, 1 over square root n times square root n. So that's an identity, and that's evaluated at k. So here we have a square root L. Now let's go back to the original periodization. So this is the periodization of f hat with period 1 over h. And okay, so and then we discretize at endpoints with step size 1 over L. So in the short but complicated notation, I would have to have a 1 over square root L here. That comes from here. So this computation or reinterpretation of the Poisson summation formula gives us a handy formula. Discretization of the periodization with period 1 over h, step size 1 over L, endpoints, is equal to the discrete Fourier transform of the periodization with period L, step size h, endpoints. So that's just, well, okay, I don't know whether you get it at that pace. But now comes a decomposition of the error into time frequency components. So this is the error. So actual Fourier transform evaluated discrete set, step size 1 over L, n values. Here is the result of the numerical procedure, discrete Fourier transform. So I insert periodization, okay, here and here. Nothing has changed, triangle inequality. Now I use this identity. So I plug in this formula on this side. So that's an identity. And what we see is here, we have twice the discrete Fourier transform. That's a unitary matrix, and I can delete it because here I have the 2 norm. So what's left here is I have f hat minus its periodization, and then I do something to it. So here I have a frequency analysis. So here comes the pure Fourier transform. On this side, it's a time component, f minus the periodization. And then I sample and take values, okay? So before I stop, let's spell this out and see. So I have the periodization of f evaluated at jh minus f evaluated at jh. So spell this out. I should have written L here. So this is a sum over m, and I subtract the value with m equals 0. So what I get is a sum over all integers m non-zero. So if I write this, well, it's just the L2 norm of this difference over the j's in this index set. I get this here, and now you see how decay conditions come in. So I just plug in the assumed decay, and then I continue. The only point I want to make, J is between negative n half and n half. So J times H is less than NH half, less than the length of the sampled interval half. Whereas here, I have M times L. So whatever I have here or here is a value of F outside the sampled interval L half. And that's how the decay conditions come in, both on the time side and on the frequency side. And now you plug in the decay conditions and do some estimates. So that's something all of us can do. So I just wanted to show you how this analysis involves Poisson summation formula, periodization, and the unitarity of the Fourier transform. That's, I think, where we got an advantage over just doing trapezoidal rule and truncation error. So after this excursion into a mathematical proof idea, let me recall our main result. Polynomial decay in time and in frequency, and some adjustment gives you an error estimate, length of the sampled interval to the negative alpha, plus step size to the beta. Alpha and beta related to the decay estimates. So that's a result. And you might now say, but wait a minute. We want to compute the Fourier transform, and we make assumptions about the Fourier transform. That's not fair. Well, if you don't like that, even if you do numerical integration, all the error estimates involve smoothness of F. And so we could say, okay, we know something about the decay of F, and we know something about the smoothness of F. And our assumption would be F has M derivatives, the integrable derivatives. Well, if you take the Fourier transform, that amounts to decay, polynomial decay of order M. And so this is just a slightly stronger condition, and you get the same error estimate. So the decay condition on the Fourier transform is just a matter of smoothness, and of course, the discretization and the error in the discretization depends on the smoothness. So what you notice is I have three parameters, H, L, and N, and here occur two parameters that you could choose, say, almost independently via N. And what you would like to do is you would like to choose these two contributions to the error. They come from the two periodizations in time and in frequency. You want to choose them to contribute equally to the error. So you choose the parameters so that they are of, say, same magnitude. If you do the arithmetic, then L is to the order n to the beta over alpha plus beta. And the step size is h, so it should be n to the negative alpha over alpha plus beta. So L to the negative alpha gives you this here. N to the beta gives you the same. So if you choose these two parameters appropriately, then you get an estimate of the error in terms of the number of samples involved. Number of samples involved tells you how you choose the step size and the length of the sample interval. You see again, this is symmetric in time and frequency. You could do that any way you want, but this is the optimal choice of increment and length of sample interval. Okay, now comes numerics, and for the numerics, so we would wanted to test this error estimate on some examples to see, are these estimates optimal? The numerics is not completely trivial because you need a function that you can evaluate exactly. You want to evaluate the Fourier transform exactly. Otherwise, you already make approximations when you plug into the formula for the error. And both the function and its Fourier transform must have the precise polynomial decay that's in the theorem. That's not a completely obvious exercise how to construct such functions. Usually you know the function and its decay, but you have a problem with the Fourier transform. You have a Gaussian, well, that doesn't, it's too strong an assumption for our theorem. So we constructed a function in a shift invariant space generated by a B-splines. So I don't know in how much detail I should go through. We take a B-spline of order B. Its Fourier transform decays exactly polynomially to the order B. B-spline has compact support. We choose coefficients, very easy coefficients, powers of 1 over 2k plus 1. And so we have functions of this form. Coefficients that decay polynomially to the order A, and the B-spline has compact support. And so these are our candidates. The Fourier transform is some trigonometric series times the cardinal sign. So this has compact support, so the function decays the same order as the coefficients. This is a Fourier series. It's periodic, it's bounded, so the Fourier transform decays like 1 over psi to the b. So decay conditions are okay. Now, we can evaluate this exactly because that's a finite, locally finite sum. No problem with that. Now, when you look at the Fourier series, so with a equal 1, the Fourier series is just characteristic function, periodized, plus something at the boundary. If you take powers of these coefficients, you get this function here convolved a times. For example, for a equals 2, you could just get the absolute value on the unit interval and then periodized. So this is a class of functions that work out perfectly. You can evaluate both function and Fourier transform, and they have the precise decay of the theorem. So if you have this decay estimate, you make a log-log plot, because in the log-log plot, you would observe a linear decay when the number of samples, the logarithm of the number of samples is your parameter, and you do that against the logarithm of the error. So we should observe a decay or a slope, negative slope alpha beta over alpha plus beta. That's exactly what we observed. And then we compared to what I'd call the ignorance choice, because if you say, don't pretend you know nothing about the function and its Fourier transform, then you would do a symmetric choice. So the sampled interval has length squared n. The step size is 1 over square root n, so h. And so this means you have n samples. In that case, if you plug that into the error estimate, your error is to the order n to the negative. And then you would have minimum of decay in time, decay in frequency, half. So that's a much weaker estimate than this here. So here first, for this class of functions, these are the error plots. So we go up to 2 to the 20. So that's roughly 10 to the 6 samples. And here are the error rates. They're perfectly linear in the logarithm of the number of samples. The slopes are as predicted. This is absolutely non-trivial numerics, and Martin should get a prize for that, I think. I would not want to touch that. And so this is a verification on example. You cannot do better than these error estimates. Then we took a few of these functions with symmetric decay in time and frequency. So we take alpha, so the alpha, here we have a equals 2, b equals 4. Oops. So the alpha would be 3/2, beta would be 7/2, and so the decay rate would be 21 over 20, whereas the minimum of these two is 3/2. So the ignorance choice gives you a decay with slope 3/2. The adaptation where you choose the parameters in the optimal way gives you a slope 21 over 20. So if you put in the knowledge about the function and its smoothness, you get a much steeper error curve than when you just do the natural symmetric choice. So let's just do an example. So that should be convincing. But let's read this from a different point of view. If you say, I want an error 2 to the negative 15, so that's about 5 to 6 digit accuracy. Now on this plot, if you go here, that tells you I need about 2 to the 12. So that's roughly 4,000 samples with the optimal choice of parameters. If you do the symmetric choice of parameters, you need 2 to the 17. So between 2 to the 12 and 2 to the 17, it's 2 to the 5, about a factor 30. So in order to achieve 5 to 6 digits accuracy, this would be 4,000 samples, and here would have 2 to the 17. That's, I'll say 100,000 samples. That's significant already for an accuracy of 5 digits. And now we played this through for 2/5, so more asymmetry in time and frequency. Always with length squared n, h 1 over squared n. So sorry, the p was in the paper. For period, now it's length. So here it's for 3/5 when you have some asymmetry. In here it's 5/2, so decay 1 over x to the 5, but the smoothness is only twice continuously differentiable, and somehow lack of smoothness behaves a little bit worse when you do it numerically. But in all cases, you see this distinction between, say, generic choice and choice adapted to your knowledge of decay in time and frequency. So now let's see, I have about 3-4 minutes. So now this is sort of an encore. I formulated the theorem in terms of polynomial decay. We love amalgam spaces in Vienna, so we actually had slightly different spaces. So the amalgam space, locally bounded continuous on it, and globally those local suprema are in a weighted L2 space. So that would be the standard notation. The alpha tells us how these local suprema decay, and it's an L2 decay. And if we use this version of decay of a function, then we have, if f is in this amalgam space, f hat is in the amalgam space with parameter beta, then we get decay, or the decay of the error that we have seen before. And polynomial decay is a simple consequence because we'd have the embedding precisely for this range of parameters. So that would explain why we would have to move from the parameter for polynomial decay to something else. One can do lots and lots of things. One important thing is, and when you talk to numerical analysts, they always say, oh, these are just asymptotic estimates. We need precise estimates. Who knows, if the asymptotics works only at 10 to the 10, we cannot use it. So we did something with precise estimates. So here is some constant. So basically it's about 4 to the s. And if you assume that f is in the amalgam space with parameter alpha, Fourier transform decays and is in the amalgam space with parameter beta, you multiply these norms with these constants and choose correctly, then, so L is not only to the order of n to the beta over alpha plus beta, but with this precise constant, step size as well, it does not really matter. Then the error is just this here. So it's the same asymptotics, but the constants now depends in a precise way on the amalgam space norms of f and f hat. So if you have some access to these constants, then you have a precise non-asymptotic error. So the results are not asymptotic results. This is really this holds for arbitrary n. So you could do other decay conditions. So sub-exponential decay of f, and f hat leads to sub-exponential error bounds with slightly different coefficients. But sub-exponential decay gives you an L to the alpha here with a different constant here, and gives you an h to the negative beta with a different constant here. So the decay of f and f hat translates into the error estimates. Perhaps one more would be exponential decay and finite smoothness of the function. Well, you get exponential decay in terms of the length of the sampled interval, and the smoothness enters here. Now, if L is large, then basically you only see the smoothness. And then you can compare with the estimates by Stenger or by Briggs and Hansen. Last aspect, the numerical procedure, once again, is sample a function, take discrete Fourier transform, and you obtain a vector that approximates the sampled Fourier transform. Well, you're actually interested in the full Fourier transform. So what do? When you plot, you interpolate these values. You could plot piecewise linear, Or a nicer way is to you interpolate and get a smooth function. So you interpolate with the cardinal sign. So sine pi x over pi x. And it has the property that it interpolates. So cardinal sign at integers is the delta. So 1 at the origin, 0 everywhere else. So if you put in the output of the numerical procedure as coefficient into a cardinal sign series, well, at k over L, you get exactly the yk, you get exactly the output of the algorithm. And the message now is, okay, if you interpolate the output of the numerical procedure and compare to the actual Fourier transform, then the error in the L2 norm of R is exactly of the same order. We can put in the amalgam space norms. We get exactly the same order. If you interpolate linearly, say with a hat function, then you have saturation, and the alpha should only be from 1/2 to I. So whatever you do, you get the same error rates as for the discrete version. Anything else? I think I should stop here. So you could ask for minimal condition when this procedure converges at all. And I think with that, I just summarize. We asked us a very natural question that, interestingly, nobody had looked at with, say, general conditions on F and F hat. And we found explicit and precise optimal error estimates. There's a benefit for numerical procedures. If you fine-tune the step size and the length of the sampled intervals, you get either better accuracy, or for given accuracy, you require fewer examples. And if we talk about 10 to the 6 samples or 10 to the 7 or 8 examples, that might make a difference. I think we could do that because we used our favorite tools: time frequency analysis, amalgam spaces, and shift invariant spaces. Paper has appeared recently. You can see it in a much nicer version. And with that, I want to say thank you for, 55 minutes. Thank you.
All right, let's smash those reaction buttons.